We're going to write down a model, an exponential model, for the amount of carbon dioxide in the air at this observatory in Hawaii. And we're going to do it in parts per million, T years after 1970. So we have a couple of data points. First, we know A naught is 325. We can fill that in the model. And then we know in 2020, there will be 413 parts per million. That was our other data point. So we plug in T equals 50, and then we know A is 413, which gives us this equation. 413 is 325 times 1 plus R to the 50. We're wanting to solve for R first, so we're going to take the 50th root of both sides after we divide both sides by 325. So now we have the equation, an equation of the form constant equals base raised to a power. We're wanting to solve for the base though, so just take the 50th root of both sides to solve for 1 plus R. And then to get R, just subtract 1 from both sides. Once I have this expression for R, I'm going to go ahead and plug that into the model. So if I'm doing this by hand and I can't get a decimal approximation for R, then when I plug in R into the equation, I have 1 plus, and then this fraction in parentheses, raised to the 1 over 50 minus 1. So I have a plus 1 in the front, a minus 1 in the back. Those cancel. Just gives me 413 over 325 raised to the 1 over 50 there in the parentheses. But if I wanted the decimal approximation, if I had a calculator on me to get it, then that stuff inside the parentheses becomes 1.0048. Now we want to predict the year in which the amount of carbon dioxide will reach 450 parts per million there in Mauna Loa. So we'll plug in 450 for A, the amount, and we don't know the time, so we're going to leave that as T, and now we just need to solve for T. So we know how to do this. First, get it in the form constant equals base to the exponent by dividing both sides by 325. Then we can either immediately write it using a logarithm, or we can take the natural log of both sides. I'm going to use the natural log approach. That's more common, especially as you get up into higher mathematics. So I'm going to do it that way. I'm going to use the property of logarithms then to bring the t down in front on the right side. And once I do that, on the right side, I'll just have t times a number, that number being natural log of 1.0048. So I'll divide by that number to solve for t. And if I'm just doing this by hand and I don't need a decimal approximation, I can stop right there. If I do have a calculator on me, punch that in, I get 67.96. That's the number of years after 1970 when we'll reach 450 parts per million. So that'll be right at the end of 2037. And then in part C, we're asked to rewrite the model in this different form using a base of E instead of a base of 1 plus R. So if we wanted to do this quickly, we could just calculate K equals natural log of 1 plus R. But if we kind of want to do it from scratch, we know 325 is the initial amount, so we'll plug that in. And then we know that the amount will be 413 in 2020, so that's when t equals 50. And I made a mistake here. When I was writing this out, I plugged in 50 for k instead of t. So that should say 50 times k in the exponent. I'll go back and fix that in a minute in the video. But we're going to divide both sides by 325, solve for the exponent as usual, take the natural log of both sides, use the property of logarithms to bring the exponent down in front. We know the natural log of e to the 50t would be 50t. Or if you want to see it this way, natural log of e is 1. So either way, we get the same equation. And then right around here is where I'm figuring out that I plugged in 50 for k instead of t. And what clued me into that is that I shouldn't already be solving for t. I just wanted to solve for k here so that I can write down what the model is. And then in part D, we'll solve for t. So change all of those k's to t's. And then we get an expression for k. If I don't have a calculator on me, this is good enough. If I do have a calculator, I'll go ahead and punch that in. The decimal approximation of k comes out to be 0.00479. And so we can finish up our model by plugging that in for k. And then in the final part of this problem, we're asked to find, again, the time t that it takes for the amount in parts per million to reach 450. We're trying to find the year that happens, so that means we're solving for t. So plug in 450 for the amount and plug in, well, leave t like it is, because we're going to solve for the t that makes that happen. Divide by 325 to get a constant on the left equals a base raised to an exponent. Take the natural log of both sides. On the right, the natural log of e raised to anything is just that anything, that power that was already there. Because you're asking what power do I raise e by to get e to the 0.00479t. The power is already given to you there. Or you can think of it as bringing the exponent down, and then natural log of e is 1. Then solve for t by dividing both sides by that number, 0.00479. And that's the year after 1970. If I want a decimal approximation for the year, I'll plug that into some calculator. The decimal approximation comes out to be 67.94, which is good. That's almost exactly what we got in part B. So again, we'll say that you'll reach 450 parts per million. We're making a prediction. This will happen probably right at the end of 2037.